Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 8, 2025, so just about 6 days ago. This paper introduces a method that achieves more than 2.5 times the inference speed of popular models, like Llama 3. The paper is titled, Diffusion LLMs can do faster than AR inference via Discrete Diffusion Forcing, and as we'll see, the speedups are quite significant. This work focuses on a new strategy to make Diffusion Large Language Models, which generate text by refining random noise in parallel, faster than traditional autoregressive models that generate text one word at a time. Also, the authors shared their code on GitHub, and it's a great resource for anyone wanting to dig deeper. You'll find everything you need to reproduce their evaluation results, plus simple generation demos to see the speedup for yourself. They even include instructions for their preliminary VLLM integration. On Hugging Face, you'll find LoRa adapters for the 7 billion and 8 billion parameter models, along with the official code you'll need to try them out. Okay, and these charts really show the impact of this new approach. Looking at the results on the left for the GSM 8K math benchmark, the model using this new method, shown in blue, achieves nearly 120 tokens per second. That's a massive jump, more than 2.5 times faster than standard autoregressive models like Llama 3. We see a similar, though slightly smaller, speed up on the right for the human eval coding benchmark, hitting over 80 tokens per second. Now, this is really interesting. These plots show the trade-off between throughput, or speed, and performance score. In both charts, for the GSM 8K and MBPP benchmarks, the blue line represents the new D2F model. You can see it creates a much more favorable curve, operating at higher speeds and achieving better scores than the original model, shown in gray. The different points along that blue curve represent different settings, letting you tune for either maximum speed or peak accuracy and still stay ahead of the competition. Alright, so this diagram really breaks down how the training works. The core idea is an asymmetric distillation process. You have a pre-trained teacher model on the right, which has a full bidirectional view of the text. Then, on the left, you have the new student model. It's trained to match the teacher's predictions, but with a crucial difference. It uses a blockwise causal attention mask. This special mask only lets the model look backward in blocks, which is the key to enabling KV cache and achieving that incredible speedup. Alright, so moving on to inference. This visualization shows the pipelined parallel decoding process in action. You can see the model decodes a pipeline of text blocks all at once. A new block is added dynamically, and it starts in a semi-activated state, shown here in light purple, which means it decodes more conservatively. Then, once enough of the previous block is confidently decoded and cached, which you see in gray, the next block becomes fully activated. This fully activated state, in dark purple, lets the model decode multiple tokens much more aggressively, which is a key part of the speedup. Okay, and this table lays out the hard numbers, comparing different acceleration methods on the LLaDA Instruct 8B model. We're looking at metrics like tokens per second, latency, and the final quality score across 4 different benchmarks. The results are pretty dramatic. For instance, on the MBPP programming benchmark, the new D2F LLaDA model achieves a massive 52.9 times speedup, jumping from less than 1 token per second to nearly 48. And it does this while maintaining a comparable quality score, which is really the key takeaway here. So, putting it all together, the big takeaway is that this hybrid approach successfully breaks the inference speed barrier for diffusion models. By combining the efficiency of KV cache with parallel decoding, the authors have created a model that's not just faster than other diffusion models, but significantly faster than leading autoregressive models too. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.